And we're very pleased to have Dr. Casey Berger from Boston University, or as we call it, BU. And although, I don't know, are you in Boston now?
Not physically located in Boston. I graduated from UNC just, well, gosh, 6 weeks ago now. So I'm still hiding out in North Carolina until it's safe to move.
Right. Okay. Well, you know, things are going down in Boston and going up in North Carolina, so it might be a good time to move.
True.
Anyways, a very interesting topic we're going to hear about today, having to do with something called complex Langevin, and it's one of the primary methods that's being explored in terms of dealing with the sign problem, which comes up in a lot of contexts. I'm sure that Dr. Berger will give us some examples of where these things appear and why it's important to solve this problem, and why it's something that everybody wants a solution for. So with that, I welcome Dr. Berger to give her talk.
Great. Thank you so much, Professor Gate, for the invitation to speak today. Thank you all for coming to my virtual talk. This is not going to be a full hour and a half. It's just going to be a sort of 40-ish minute lecture. So, and I invite lots of questions. If you have any questions, please feel free to ask them. But I will be talking today about the work that I performed over the past few years, primarily as part of my PhD at UNC Chapel Hill. And it does involve circumventing the sign problem using a method called complex Langevin, and in lattice field theory, but specifically in rotating bosons. Okay, so I'll start with an outline and give you a sense of where I'm going today. First, I'll give you some context on the specific system that I'm applying this method to. That is superfluids and what happens when you subject them to rotation. Next, I'll discuss the computational challenges to studying these kinds of systems, namely the sign problem, and where it arises in quantum many-body physics. So then I'll provide a little context on the numerical method that I use to study the system. This is the complex Langevin method. I'll move on then to applying the method to the system of rotating bosonic systems. And as I get into this, I'll address some issues that do arise in applying this method to rotating bosons and how we can use other theoretical tools to shed some light on what's actually happening here. And I'll discuss some of the computational methods that I'm using to push this further and get higher performance, because this has actually turned out to be a very crucial part of this process. And finally, I will discuss what I've learned from this process, how we can use that knowledge to make some progress in this field. But first, a PSA, because we all need a little levity in these challenging times. My work focuses on bosons, but let's all be good fermions for the time being and practice social distancing. This is very important right now. Okay, so on to that context that I promised. The simple definition of a superfluid is a fluid which flows without friction. This means that some conserved quantity is transported with no loss of kinetic energy, and usually this conserved quantity is a particle number. This is a really fascinating topic. It's actually an example of a macroscopic quantum phenomenon very closely related to superconductivity. So you'll see these two things mentioned very frequently together, the question of superfluidity and superconductivity. It does occur naturally in helium-4 and helium-3 at low enough temperatures, and also perhaps in the core of neutron stars, which is a sort of an interesting element of astrophysics that's being explored. And of course, in experiment, these superfluids can be made and manipulated with supercooled atoms. And in labs, you can actually do some really interesting stuff where you can tune these interactions between the atoms and basically create any kind of system that you want to explore. So that's a really excellent, flexible, sort of experimental technique that is being used to study this kind of physics. So the frictionless velocity flow is actually the point that I want to return to here because it leads to some really interesting behavior relevant to the system that I study. So what actually happens when you add rotation to a superfluid? So the velocity field of the superfluid is the gradient of the phase of the condensate. So really what that means is it has no curl. If you take the curl of the velocity field, you get 0. So if you add rotation to the fluid, you are imparting some angular momentum to the system, and it has to go somewhere. And since it can't go into the fluid's velocity field itself, this causes the superfluid to generate localized singularities. And all of the angular momentum that you've imparted into the system exists at the boundaries of these singularities or vortices. Um, and you can actually calculate how much angular momentum is in the system by looking at the circulation around each vortex. The circulation is quantized. It obeys this relationship where this n represents the quantum number. So this is something that you can measure. This is something that you can predict. And it's a very interesting quantum behavior in these rotating superfluids. All right, so what makes up a rotating superfluid? What is it made of? So these systems have four elements. They're composed of bosonic particles with a non-relativistic dispersion, which just means moving much, much slower than the speed of light. These particles are confined with a harmonic trapping potential, and this mimics the way that an ultra-cold atomic gas is confined in the lab with magnetic fields, for example. The particles must also be interacting at a very close range, a repulsive contact interaction, and we represent that using a delta function. And finally, of course, they must be rotating. It's a pretty crucial component to our rotating superfluid. So studying rotating bosons can actually help us understand situations that arise across a very large range of physical scenarios. It can shed light on the way superconductors behave in a magnetic field. It also appears in pulsars. So I mentioned that neutron stars have a superfluid core. And if those neutron stars are rotating, then you have a rotating superfluid inside of this neutron star. So we don't still fully understand what happens in that. It can also help us describe the behavior of rotating nuclei. And then, of course, I mentioned those laboratory experiments that are extremely flexible and can create just about any situation that you'd want to study. We can compare and contrast our results with those lab experiments. And often what the material that's used in those is a superfluid helium or some other dilute atomic gas. Okay, so we've talked a little bit about what a rotating superfluid is and where you can find it in nature, but how have physicists actually studied it? Way back in 1949, Lars Onziger predicted that if you forced a superfluid to rotate, it would form vortices. And it took 30 years, but in 1979, this behavior was first observed in rotating superfluid helium-4. So you can see here the creation of these vortices, and the number of vortices actually increasing as the angular momentum increased. Over the next few decades, there were a number of advances in experimental techniques, which led to a huge number of studies of these rotating superfluids in other dilute atomic gases, including this observation that you see here of vortex lattices, like this one, where you can see this sort of triangular lattice structure in the vortices. So it's worth mentioning as well that this same behavior can be seen in fermions. Fermions can pair up in a process called Cooper pairing, which leads to superfluidity in fermionic gases such as helium-3, which I mentioned earlier. We can see, in fact, the same vortex formation and the same lattice structure in a rotating fermionic gas like this image from a 2005 experiment. However, since fermions must pair up into bosonic groupings of particles in order to exhibit this behavior, it is still primarily a bosonic behavior. So from this point on, I'm just going to refer to this all as bosons. Okay, so what theoretical progress has been made on these systems? I've shown you some pretty pictures from experiment, but let's talk a little bit about what's happening on the theory side. So unfortunately, theoretical progress has been somewhat slower than experimental progress in this area. And this is because we aren't able to use the usual computational methods for many-body quantum systems, specifically quantum Monte Carlo. So quantum Monte Carlo derives from the path integral formulation for quantum mechanics. In this formulation, the path integral is an infinite dimensional integral over the all of the field values of the exponentiated action. So the action here is a functional of the fields, and it encodes all of the dynamics of the system. And we can actually compute observables using this path integral formulation by doing this infinite dimensional integral. So we treat this exponentiated action like a probability distribution. So I'm actually getting ahead of myself. So if you calculate the observable exactly, right? So if you look at this naively, you have an infinite dimensional integral, and this doesn't seem like a really great sort of setup for doing a computational problem, because if you want to calculate an infinite dimensional integral on a computer, you need infinite memory or infinite time, and we don't have either of those. But quantum Monte Carlo has a great trick. It allows us to evaluate this system stochastically, and it basically allows us to treat this exponentiated action like a probability distribution and take samples from this probability distribution. So in this case, we can calculate observables up to some statistical uncertainty, and that uncertainty will depend on the number of Monte Carlo samples that we actually take. All right, so what does this actually look like in practice? Let's start with a really simple quadratic action. So A times phi squared, where phi is our field. This action has a probability distribution that just looks like a Gaussian. And then we can calculate an observable if that observable can be written as a function of the fields, and we just have to do a simple weighted sum. So this is what the probability distribution that we would be sampling over actually looks like. It's a very nice, well-behaved distribution. It's all positive. It's very easy to sample using Markov chain Monte Carlo methods. We would love if all of our probability distributions looked like this. Unfortunately, this is not always the case. So let's look at another example, which will show us what happens if we don't have a well-defined probability. So let's take that quadratic action and we add to it an imaginary term. So now we have this a phi squared, and now we have another quadratic term, but it's multiplied by I. So this will give us a probability distribution which has a Gaussian envelope, but then it also has these two trig functions which will oscillate between positive and negative values, and we have this imaginary term. So what does this really mean? I mean, this isn't what we expect when we look at a probability distribution. So this is what that probability distribution would look like. And it should be really clear from this plot that this is not actually a probability. This reveals some of the limitations in quantum Monte Carlo methods. We can only use them if e to the minus s results in something that is positive definite. And unfortunately, a lot of the systems that we're interested in look a lot more like this distribution than our nice Gaussian from a few slides ago. So we've seen that quantum Monte Carlo has some limitations, as useful of a method as it has been. Certain systems are just not accessible using these methods. And when we have systems with a complex action, we say that these systems suffer from the sign problem. And in fact, systems that suffer from the sign problem are everywhere in physics. They appear in the repulsive Hubbard model, the nuclear three-body interactions, rotating neutron stars, which I've already plugged a few times, lattice QCD with non-zero chemical potential, so with any quark matter, and then some, but not all, of the systems that can be constructed in the lab will also suffer from the sign problem. And this is not only a pervasive problem. I mean, we see that it appears across a huge range of interesting systems, but it's also an extremely difficult problem. In computer science jargon, this is called NP hard. What this means from an algorithmic perspective is that we don't expect any generic polynomial time solution to exist. And what this means for computational physicists is basically just we need to find some way to work around it. So that brings me to the method that I use in this work. This method is called complex Langevin. It's a way to get around the sign problem, and it specifically works when we're trying to treat systems that have complex actions. So first, let's discuss the Langevin method more generally, look at how it works for a system which is entirely real. So just like with quantum Monte Carlo, our goal is to compute observables, and we compute observables in the same way. But instead of sampling from a probability distribution, we instead evolve the fields themselves using a stochastic differential equation, which is called the Langevin equation. This equation evolves the field using a derivative of the action, which you see here. That's the physics of the problem. And then a Gaussian distributed white noise term. So that's the stochastic element of the problem. And after quite a lot of algebra, which I won't bore you with, we find that this obeys the Fokker-Planck equation. And that just means simply that after a very long time evolution, the method converges to a set of field values. So phi converges to a set of phi's which are distributed according to e to the minus s. So what we've done here is now we can just perform a simple time average to calculate the expectation values of the observables. What this means is we've achieved the same result of weighting our fields according to e to the minus s, but we don't actually have to treat e to the minus s like a probability distribution and sample from it, which is where our sign problem was arising. Okay, so I mentioned that this was involving lattice field theory, but the process that I've described so far sounds a lot like a continuum process. So we can actually discretize it and put it on a lattice and solve it that way. So what does this actually look like on a computer? The first thing that we need to do is represent space and time as a finite lattice. So here's an example of a 2x2 spatial lattice, or sorry, 10 by 10 two-dimensional spatial lattice. So at each site on the lattice, the field value is specified. And then we need to account for time. So this will add an additional dimension to our lattice, like this. Now, what we call time in non-relativistic calculations is actually a way to determine the temperature of the system. We're not doing dynamics, so this is not a time-evolved system. This is actually a static system where the time is related to the temperature. And in fact, it is proportional to the inverse temperature. So the size or the extent of our time lattice will tell us how cold the system is. And this is going to become important as we try to create sort of a quantum system. Okay, so now that we have our space-time lattice, we want to actually evolve these fields at each site on the lattice, and we do this using discrete steps in this fictitious Langevin time. And we do this so that the entire space-time lattice is updated at each step in Langevin time. So we move forward in Langevin time, we evolve the entire space-time lattice, we move another step, we evolve the entire lattice, et cetera, et cetera. So at each of these Langevin steps, we also want to calculate the observables that we're interested in and save them. And we just repeat this process for as many samples as we want to take. So at this point, it's really a question of balancing computational resources with the desired precision, because just like with quantum Monte Carlo, the variance on our calculation will actually decrease with the number of samples we take. So the more samples we take, the more computational time we need, but also the better an answer we get. Okay, so this is what the Langevin evolution of the fields actually looks like, where we're starting to compute the average after some thermalization time. So we let the system sort of equilibrate, and then we start taking our average. Okay, so that's the real Langevin method, but what happens if we have complex numbers? We're dealing with systems that suffer from a sign problem, so we want to be able to deal with complex valued variables. And it turns out we can actually extend this method to a complex field so that phi now has a real part and an imaginary part. And our action, S, will now also have a real part and an imaginary part. So this lends itself really well to the situations that we want to study, which will have naturally complex actions. The resulting stochastic differential equation then becomes two coupled stochastic differential equations, one for the real part of the field and one for the imaginary part of the field. And the drift function, this kr and ki, this is what guides the field evolution. It's just a complex derivative of the now complex action. And we still have this Gaussian distributed white noise component of the SDE. Okay, so we can do that same long time evolution that I showed you before for both fields. So in blue, we have the real field value as a function of Langevin time, and in red, we have the imaginary field value. And importantly, we can see here that the imaginary part averages to 0. This is really crucial because we don't want to be taking expectation values of observables and finding that they have an imaginary part. That's the entire point of this, right? Is that when we measure things in the lab, they're entirely real. So we want this to happen, and this is always a good sign that the method is working. Okay, so let's take a look at what this actually looks like in action. So one of the first examples, a little historical sort of background here of the complex Langevin method, as applied to quantum field theories, was on the relativistic Bose gas. So the action for that system looks like this. You don't need to concern yourself with the details of the action. What really matters is that when mu, the chemical potential of the system, is greater than 0, this action is complex. So it has a sign problem. We need a method like complex Langevin to calculate the observables. So we can discretize the action. Once we do this, we can derive our drift function for the lattice, and then we can run the simulation exactly with the algorithm that I described before. So we ran the simulation and compared it with some results from a paper published in 2009 by Herod Arts. This is the density of the system as a function of the chemical potential. And we used, so this is relativistic physics in this case, so Nx is the spatial lattice extent and Nt is the time lattice, and they are all, so it's 3 + 1 dimensions, and each direction has 4 lattice sites. And we actually found that our results showed really good agreement with the results of the paper, with some slight differences, which we think have to do with differences in our calculation of the thermalization point and the autocorrelation of the simulation. But what's really important is that we see here the same qualitative behavior where the onset of Bose-Einstein condensation occurs at critical chemical potential for the relativistic Bose gas. And here are the results for a slightly larger lattice. We can see, again, really good qualitative agreement where this critical chemical potential results beyond the critical chemical potential, we have Bose-Einstein condensation. So complex Langevin has been shown to do a really good job of actually solving this problem in a case where there's a demonstrable sign problem. And so with this sort of proof of concept, we can move on to a non-relativistic system. So I'm looking, as I mentioned, at non-relativistic rotating Bose gases, which are rotating superfluids. And we can proceed in a very similar way. So as a reminder, this is the system that we're looking at with complex Langevin. This is the action. It is composed of slow-moving bosons, a harmonic trapping potential, some angular momentum field, and a delta function contact interaction. So before we solve the full system, we want to test our method against something that's exactly solvable. So we want to make sure that our method is accurately reproducing something that has no sign problem. So if you remove that interaction, the rotation, and the external potentials, and you just have some slow-moving bosons, this is something that can be calculated analytically and then compared with complex Langevin. So we did this, and we actually found something really interesting when we started studying this. So because we're using a complex field to represent our superfluid, we find that even before adding the rotation to the system, we already have a sign problem. So we looked at the simplest exactly solvable case, which is 0 plus 1 dimensions. So there's no spatial dimensions. We just have a time derivative and chemical potential. And we looked at what was happening here. So this is our action in this case, very simple. We just have this time derivative, this chemical potential, which when we discretize it for the lattice looks like this. And we found that the non-relativistic time derivative is actually not symmetric. Now, this is something that was known, but we hadn't really considered how it would affect our complex fields. So the sign problem actually emerges right away the moment we complexify the fields. Because what happens is you can express this lattice action using a matrix. And this matrix is antisymmetric, which means you end up with complex cross terms that do not cancel. So this only occurs with non-relativistic bosons. This is not an issue with fermions, but it's something that actually arises immediately as soon as you start using complex fields. But I will note that this is still exactly solvable. So there are some special cases where you can exactly solve something with a sign problem just because you don't have, because it's a simple enough system to solve basically by hand. And unfortunately, those systems are generally not very interesting, but they do serve as good checks. Okay, so here are our results from this 0 plus 1 dimension free Bose gas. And you can see the dotted lines are the exact solution for the density, and over here the field modulus squared, so basically the magnitude of the field. You can see that our complex Langevin solution does recreate the exact solution. So, so far so good with the complex Langevin method. So let's take this to 2 plus 1 dimensions. A little more interesting, now we have 2 spatial derivatives and a time derivative and chemical potential. And we find that we get some very good results for the free gas in 2 plus 1 dimensions. So on the left, we have, again, the field modulus squared as a function of chemical potential. In red, we have the imaginary the imaginary part of the problem. It's 0 exactly with the analytical solution, and it is averages to 0 with the complex Langevin solution. And our real part is very well recreated by the complex Langevin method. This is even more apparent with the density, which is the plot on the right, where we have very, very good agreement between our method and the exact solution. Okay, so we've done some testing. We know that the method is reproducing known results. So now let's throw it into the system with rotation. So just as a reminder, this is what we're looking at. And as often happens, we discovered that this problem is actually a much tougher one to crack than we'd hoped. So these are our initial density calculations of the rotating bosonic system, the real part of the density as a function of the chemical potential. From this point on, by the way, I won't show any imaginary results. They all average to 0. It's quite boring to look at them. So just from this point on, we're just going to look at real values, the real part of the solution. So one of the things that first went wrong showed up in these calculations. And you can see here that for some rotation frequencies, these ones here in red, we get negative densities. So this is definitely not correct, right? It's an unphysical solution. You would never measure density in the lab and get a negative number. But we are actually able to use insights from a method called the virial expansion to explain this issue. So a quick detour to shed some light on what might be happening here. We compared these results with another method that we were applying to a similar system. All right, so this method is called the virial expansion. It's an approximate method, and we construct this approximation by taking an expansion, as physicists love to do. We expand the log of the partition function here in the fugacity, and fugacity is just e to the beta mu. So it's just a convenient way to express the chemical potential and temperature of the system. So this expansion is also related to the grand thermodynamic potential omega. So this is actually getting into some statistical mechanics. And the coefficients, these b sub n, of this expansion can be calculated by way of the n-body partition functions, which are much easier to calculate. And note that what we're doing here is actually capturing the n-body physics. So when we calculate B1, the first coefficient, we're getting the one-body physics. B2 tells us what happens when we have two bodies. B3 gives us three body, and so on and so forth. So the higher we go in n, the more particles we have basically accurately captured with our method. This is an approximate solution, as I mentioned, and we can determine the thermodynamic observables by taking derivatives of this partition function z, and it's valid for small little z. Unfortunately, we use z a lot in thermodynamics. So small fugacity, which means basically high temperature and low density. So importantly, this is not actually going to tell us what's happening in a rotating superfluid, but it will give us a little bit of insight that we can use on a special sort of high temperature, low density limit of our system. Okay, so how do we actually calculate these n-body partition functions and get those virial coefficients? So the one-body partition function is an infinite sum, but it actually has a finite closed form solution. So this one can be computed exactly. So we're summing over infinite all values of k. The higher n-body partition functions involve performing a sum over energies and wave functions. It looks like this. And we have to truncate these because this doesn't have a closed form solution. So we have to truncate these both in the space of the quantum numbers and in position space. We performed these sums with increasing values of our cutoff quantum numbers, and we actually found that the results converge really quickly. So we don't need to go very high in that sum to get the n-body partition function. So this is this n beta squared is part of this sum that we saw earlier, and it's the part specifically that depends on the quantum numbers. So as we increase our quantum numbers, this sum converges very quickly. We don't see much change even when we double the cutoff value in the quantum numbers. And we can see also that this n beta squared drops really rapidly in space as well. So the spatial lattice that we use to compute this can be small. Basically, what this tells us is this method is really fast and really efficient. So this is one of the benefits of approximate methods, is they're often really fast and really efficient. Okay, so I mentioned before that we could compute the thermodynamic quantities using these virial coefficients. So this one is the angular momentum expressed using these coefficients, b sub n. And we were able to calculate this just by taking the appropriate derivatives of log z. So in this case, the derivative with respect to the rotation frequency. Now, in theory, this can be computed exactly, but it does involve, again, an infinite sum. So in reality, we can compute this to just arbitrarily high precision, so arbitrarily high n. So here are some results for the non-interacting angular momentum in 3D. Again, this is our approximate system. This is not our rotating superfluid. And this is for varying trapping potentials. So for a low rotation, we see this semi-classical linear behavior, which we expect to see here. So far, so good. But then something interesting happens. So our sums, those sums over the n-body, or sums over the quantum numbers for the n-body partition functions, these fail to converge when omega z, our rotation frequency, is equal to omega trap, which is our trapping potential. And we can see that really clearly in this plot. So here we have the angular momentum plotted as a function of the rotation without scaling by this trapping frequency. So you can see what happens as omega z approaches omega trap. Our observable blows up. It goes to infinity, and it does this every time omega z equals omega trap. So what's happening here is that we have a system where the centrifugal force from the rotation is overcoming the force of the external trap. So the system is escaping. It's no longer confined by our trap. So we should be concerned only with rotation frequencies which are low enough to confine the particles in the trap. Okay, so I showed you before the angular momentum, but we can also compute the particle number by taking this derivative with respect to the chemical potential. And then if you scale the particle number by the volume, you have the density. So this is where we can compare our method with the results that we got from complex Langevin. So importantly, we see that for all powers, for all n in the virial expansion, this coefficient multiplying our power of the fugacity has a sinh in the denominator. And the sign of the sinh will depend on the difference between our trapping potential and our rotation. So let's take this little insight and look at our data again, alongside this virial approximation for the density. So we see that once our rotation is larger than our trap, this is where we start getting the negative densities. So this is a case of our algorithm giving us a mathematically valid answer, which is non-physical. And we were able to see this by calculating this approximate solution, and that gave us some insights into what was happening here. So now we know that we need to limit our parameters to ones that will give us a sort of more physical situation where we have a rotating system confined by a trap. Okay, so we're always learning, we're always improving. So we took a look as well at the angular momentum from our preliminary results in appropriate ranges of the rotation and trapping potential, and we see approximately linear behavior. So this is the real part of the angular momentum as a function of the rotation. It's approximately linear with some distortion at a really high rotation. So this is still semi-classical behavior, but we're looking for quantum behavior. What we want to see is a step function where the angular momentum becomes quantized. And we don't see this. So what's going wrong here? This is a question that we kept asking. What is going wrong? Okay, so there are a couple things that may still be going wrong. The temperature might still be too high. So I mentioned before that it was important to remember that our time lattice is related to the inverse temperature. So the lower temperature we want to go to, the larger our lattice needs to be. We are already using a lattice of n tau of 160, which is quite large. And it's taking a lot of computational resources. So if we want to go to lower temperatures, we need to improve our computational efficiency. So we also have realized that the parameters are very sensitive to each other. So we have to tune the rotation to be appropriate for the trapping potential. But we also have this repulsive contact interaction, which affects the rotation and or interacts with the rotation and the trap. Our system is very limited by these relationships between the parameters. So it's a very delicate process to tune all of these parameters with each other. And this is also a factor of the lattice size. So the size of the lattice and the spacing of the lattice will determine things like the harmonic oscillator or the scattering frequency. And we basically need to tune all of these parameters, and we need a larger lattice in order to do it. So this problem needs much greater computational resources than we've been using so far. All right, so this brings me to one of the computational tools that I'm using to start pushing this method further. This is called AMReX. So what is AMReX? It is a block-structured adaptive mesh refinement software framework. It's part of the Exascale Computing Project's Co-Design Center. It supports CPU and GPU parallelism with a variety of languages. Very flexible, very easy to use. You can learn more about it at this website. It's a really excellent framework. So what does block-structured adaptive mesh refinement actually mean? It's quite a mouthful. This is what it looks like. So AMReX will allow us to concentrate our computational resources in regions of interest. It does this using a mix of fine and coarse grids. So you can see the grid size is changing here. This is adaptive. There's no parent-child relationship. The grid structure adapts dynamically. It's a really flexible framework that allows us to sort of treat these much more complicated systems and really focus our computational resources where we need them the most. It's already been used with really great success in a number of fields in computational physics, in astrophysics, in cosmology, in combustion physics, and in fluid dynamics, and actually quite a few more. It's growing every day. If you go to their website, you can see the kind of really fascinating work that they're doing. All right, so what will this allow us to do? Applying AMReX to the question of rotating superfluids, still using the complex Langevin method, will allow us to concentrate our fine grids at the center of the trap, which is where we expect the vortices to appear first. It will allow us to scale up the lattice size greatly to approximate a continuum physics without a corresponding increase in the computational cost, because we'll be really focusing our efforts at the center of the trap where the interesting things will happen. We hope that this will allow us to observe vortex formation in the density profiles of the system, as well as give us enough room to vary those lattice parameters within appropriate limits, because the majority of the system is going to be virtually empty. The density of the system is going to be close to zero for most of the physical space. It's really just in the middle where interesting things are happening. Okay, so we want to apply AMReX to increase our computational power and go to larger space-time lattices. We have some early results already. We're just getting started with this, but we're already seeing massive speed up in the algorithm using AMRX's parallelization. So here are some figures of merit. You can see the number of cells advanced per microsecond, per number of cores, or as a function of number of cores. And we're actually very close to ideal scaling, even with expensive I/O. So saving these observables every 10 steps is a lot more frequently than we need to. We're still seeing very good scaling. So on the left, we actually have the CPU scaling, and on the right, GPU scaling is even better. And this is actually even before applying the adaptive mesh. So this is just putting a completely uniform lattice in AMReX and then using their parallelization. So this is a really appropriate problem to use this method for. And I'm very excited to be moving forward with this. So things that can be done now that we have this really excellent computational tool to use. We can decrease the temperature of the system, which will increase the temporal lattice, and we can also increase the spatial lattice. So we can do both these things at once. It's no longer prohibitively expensive because AMReX will allow us to do this without sacrificing the computational resources. We'd like to see triangular vortex lattice structure in the density. So way back at the beginning of the talk, I showed you this picture. You can see these triangular lattices basically made out of the vortices. This is the lowest energy configuration. So we want to see, as we go to really low temperatures, not only do we want to see vortices appearing, but actually arranging themselves in a triangle. We also want to look for discontinuities in the circulation. So the circulation I mentioned at the very beginning is this quantized circulation around the boundary of a vortex, and you can calculate it in the following way. It's basically a line integral around a loop. You can do this on the lattice by just sort of taking a square loop and going around it and calculating this integral. So this is something that we can compute using the complex Langevin algorithm, and we can actually find quantized angular momentum in this way. Okay, so in summary, complex Langevin is a very, very useful method. But rotating superfluids are proving to be a much more complicated system. They're extremely sensitive to the parameters. To get to lower temperatures, we need much larger lattices. This results in a much greater computational time needed. And my current work includes collaboration with AMReX to maximize the efficiency of our algorithm and really scale up those lattices so we can start to see some exciting results. So we're not there yet. We have not completely circumvented the time problem, but we have learned a lot about the system, and I really believe that this will help us crack it one day. If you are interested in learning more about complex Langevin, I have written a review paper. It is on the archive. It's currently under review, and hopefully will be published soon, but it's all up there on the archive. Probably more than you ever want to know about complex Langevin. But if you would like to read it, and if you have more questions, please feel free to contact me. Huge thanks to everyone who supported me, my supervisor, Rich Brower at BU, my group at UNC Chapel Hill saw me through my PhD, and of course, my wonderful collaborators who have been there throughout this whole process. So thank you all for listening. I really appreciate you taking the time out of your evening to listen to me blather about complex Langevin, and I am happy to take any questions that you might have.
Awesome. Thank you so much, Dr. Berger. We were happy to have you. Say some people don't have mics, so they might have to type out a question.
Okay.
There was one in the chat, by the way. I don't know.
Yeah.
Not every person.
Are you able to see the chat?
I think I need to end my slideshow to see the chat. I am new to WebEx. Guess I'll unshare my screen. Okay, now I can see the chat. Okay. Okay, so a question about instability. So the question is, I've heard there can be instabilities for non-interacting bosonic systems that are actually stabilized by introducing interactions. Yes, so this is sort of what I was saying about all of these parameters being really sensitive to each other. And yes, actually, so bosonic systems are extremely unstable if you have an attractive interaction, but a repulsive interaction will stabilize them. So that actually is helping us to make things a little bit easier to deal with. But it also sort of spreads out the density of the system. So as you increase the repulsive interaction, the particles want to spread out, which will kind of come up against the trap, right? So if you have too small of a trap and you have too large of an interaction, you're actually going to end up sort of pushing things outside of the physical constraints of your trap. So yeah, it's a lot of parameters to balance, and really getting a much larger lattice to work with will help us have a little more flexibility there. So great question, though.
So does AMReX does it make use of parallelizing by like splitting up the lattice in between like different nodes on a cluster or GPUs, CPUs? Okay.
Yes, that is exactly how it does it. So it'll split up, and you can fiddle with sort of the grid sizes you want to use and that kind of thing, and find sort of optimal grid sizes. But it's really flexible. There's a lot of you can feed it a lot of sort of instructions or let it sort of automate things. But yeah, that's how it does it.
Okay, so that's what I was going to ask next. Is does it kind of take care of the message passing for you so that they all the pieces of your lattice are on the same page, I guess we'll say?
Yeah. So the mechanics of that, I'm not as. I'm trying to remember how you actually set that up, but yeah, so it sort of, you can feed it a bunch of instructions about how you want to do things, and then it handles all of the communication between those after you've given it those basic instructions. So it's pretty user friendly in that way.
Okay, gotcha.
So I had a question about the virial expansion. How far can you push that in terms of testing your numerical simulations?
You mean how far, or how much can we, how close can we get it to an actual quantum system, or?
I guess I'm wondering about the range of validity and whether there's at some point, you're kind of in the dark a little bit about what you should get from the numerics.
Yes. So you do have a fairly small range of validity in terms of temperature and chemical potential. You can go very far in n, in the number of coefficients you use, and you'll get a much more accurate number. I mean, so in theory, you can solve these systems exactly if you go all the way to infinite n, right? But we actually found that after 3 or 4 coefficients, we were converging, and the coefficients were getting so small relative to the previous coefficient that it was sort of not even worth going beyond n equals 3. But again, this does only work for z less than 1, so that restricts your temperature and your chemical potential quite a bit.
And what is the meaning of negative chemical potential?
So with bosons, you can have negative chemical potential. It's sort of a funny side effect of the field theory there. It's very strange, right? Because you don't expect to have negative chemical potential, but it is just sort of a thing that comes out of the theory. And in fact, you want to have negative chemical potential for rotating for superfluids in general.
Yeah, that's right. Yeah.
All right, looks like there's another question in the chat. With energies and configurations, yes, that is a great comparison. Okay, so with Markov chain Monte Carlo, you're often using something akin to an energy, right, to do the sampling. But the drift function, that k, which is the derivative of the action, it's very much like a force. And in fact, sometimes you'll hear people in the complex Langevin sort of field discussing it as a force that drives the evolution to a more physical evolution, right? So it is driving the physics of the system. So yeah, it's absolutely like a force. So that's a really great comparison. Ooh, okay, so this one is out of my range of knowledge. I have no idea if the Langevin equation is related to the Einstein-Langevin equation. I would make an educated guess that it is, considering the shared name and the fact that the Langevin process is a stochastic process. So I'm guessing it is related to stochastic semi-classical gravity equations. But I do no work with gravity, so I'm purely quantum, but not quantum gravity. So this is outside of my expertise, unfortunately. But it sounds interesting. It could be a cool point of comparison.
And why was it again that the time was inversely proportional to temperature? Could you go over that one more time?
Yeah, so this is a sort of an artifact of non-relativistic lattice field theory, where you actually, I skipped a lot of these steps because I didn't want to get too into pedantic details, but you end up doing a Wick rotation where you're not actually dealing with time, you're dealing with imaginary time. So you've taken, in order to resolve one of the early sign problems that arises, you actually take time to I times time, and you call it tau. So what we call time in non-relativistic lattice field theory is actually imaginary time, and it corresponds to the temperature, because you can make, then once you've taken time to imaginary time, you can actually make a direct comparison between the path integral and the partition function. And in the partition function, the role of imaginary time is actually played by inverse temperature. So it's sort of a useful mathematical trick that actually sheds a lot of light on the physics, which is kind of cool. But if you're interested in this, I definitely recommend, I can try to find some specific references, but just looking up sort of this correspondence between statistical field theory and the path integral, and sort of where that relationship appears, because it's very interesting. Yes. Lots of recommendations in the chat. Good job. Everyone coming to my aid here.
Because I knew it had something to do with like the intersection between the statistics and the field of it, but I don't do much in that, so I was just wondering. But thank you.
Yeah, sure. All right. Any other questions?
Okay, great. Well, oh, there's another question. Okay.
Yes. I do think there is some work exploring complex Langevin. Well, okay, so I know that the real Langevin equation is actually used pretty frequently in fluid dynamics to talk about non-equilibrium fluid dynamics systems. I don't know about quantum non-equilibrium quantum physics, but I imagine there is some interest in exploring that. But it definitely is used in non-equilibrium fluid dynamics. Awesome. Yeah, and feel free. I'll put my email address because it has now changed, right? Because I switched institutions. Feel free to email me. My email's in the chat if you have follow-up questions on any of this. Always happy to talk.
Awesome.
Okay, great. Thank you, Dr. Berger. And
Thanks, everyone.
And have a good rest of your evening, everybody.
Great. Take care.
Thanks so much.